Hey, we're live now. I'm coming to you from, as you can see, Arrowhead. I'm definitely live streaming from the Chiefs game tonight, so didn't want to miss the game. Hope everyone is having a good time. Anyone wants to mention anything in the live stream or in the comments, that would help just to make sure we're actually live. Okay. 18 people looks like. Good to see. So just so everyone knows, Venkat, the incredible worker he is, he's actually finishing up another presentation right now. So he'll be joining us at 5:30. So about the next 15 minutes, you'll have to deal with me. But to actually kind of cover some stuff during that time, we'll go ahead and do Java news. And there is one segment I do want to spend some time on. Cool, great. Everything coming in, great. All right, let's go ahead and share my screen. Cool. Actually, let me get everything set up. I was prepping dinner just before this, so just need to get everything good and ready. There we go. That's a better look. All right. So, of course, as mentioned, Venkat will be joining us, and he'll be talking about continuations and fibers. Really interesting subject. It's kind of one of the big changes that are coming to Java in future releases. It's not really particularly scheduled yet, but it's probably going to be really big. Kind of doing a workshop right now on Kubernetes, but in kind of the way how Kubernetes and containers have kind of taken over everything, there's a good chance that fibers might actually kind of be one of those big technologies that when it finally starts becoming part of the mainline Java branch, when it's released here maybe in a year or two, it could actually have a pretty significant impact. Of course, I'll leave that for Venkat, who will be able to speak on it in much more depth and authority than I ever could. Of course, welcome everyone for coming to the Kansas City Java User Group. And of course, it's great if this is your first time. Hopefully you'll be back for future meetups. And also thank you for our sponsors, IBM for kind of helping sponsor StreamYard, VMware for sponsoring our meetup group. And while we aren't currently meeting in person, YRC has been hosting us for about a year and a half before all this happened. And hopefully, maybe when we get back to normal, we can again start meeting in person at YRC. So what's happening this month? Well, the big news is JDK 15 will be released. We kind of already covered, I think, most of the stuff that's coming in JDK 15 in some of the previous segments. So definitely check out our YouTube channel to okay, I'll tell you, can't say a little bit. But yeah, JDK 15th will be released on September 15th, kind of continuing with that 6-month release cycle. The other really big piece of JDK news, though, is that it was finally moved out of Mercurial, which is a very apt name for that kind of software control management into Git and also on GitHub. So, it should hopefully make it easier for people to actually start contributing to the actual JDK itself if you're kind of interested. So definitely check that out. For other software releases, should have taken some more time to go through this. Just been very busy recently. But Spring Boot 2.4. So also kind of like with Java, Spring Boot has recently moved to a 6-month release cycle cadence. So it's a softer 6-month release cycle cadence. So like not Spring, but Java, it's like very like they'll like September 15th was kind of decided quite a while out, and like they're very hard on hitting their date. Whereas kind of based upon the blog articles I've been reading, like for example, like they'll say like, oh, we'll release in like say like September or October, November or something like that, whatever, 6 months from when Spring Boot 2.3 was released. So they're a little bit, at least so far, softer on that, but it's roughly going for a 6-month release cadence. Just kind of also, but what I've been reading from some of the blog releases and what they've been talking about, they're continuing to kind of improve their support for containerization and Kubernetes in Spring Boot. It seems to have been like a very big emphasis. I know Spring Boot 2.3 provided native support for liveliness and readiness probes, and then also graceful shutdown. And it looks like they're continuing to support like having more native support for creating Docker images. I think I saw a Twitter post on that from one of the Madura Behave on the Spring Boot team. So that's kind of something to continue looking for if your organization is moving to Kubernetes. They're continuing to improve the support, so definitely worth it to kind of get onto the latest versions of Spring Boot for that. Gradle 6.6 was also released. I guess it has support for a release flag. I'm more of a Maven person myself, but hey, it's great also that Gradle is continuing to make a lot of advances. It's always great to have that competition and 2 options available. Other news, there's a couple of conferences coming up. So if anybody's here been to devdotnext, the same team that put that together, they're putting together the jconf.dev, which will be in September 30th. And it's just going to be, it's focused on Java, but it's everything Java. Also, J4K IO is coming up October 13th through 14th. Actually, I'll be presenting there. That's what I was talking about when I was mentioning my workshop. So if you're interested, like I said, in going to Kubernetes, I actually have a workshop, Java on Kubernetes 101. So maybe check that out if you're interested in going to J4K IO. Bunch of other conferences also coming up. There's a few conferences that are sponsored by Latin American groups, JConf Peru and JConf Mexico as well. I know it has JConf in the name like this, but I think they're independently organized. They're not actually related to one another. But those are a couple other conferences coming up in the October timeframe. So the big thing here, we have about 5 minutes until Venkat will be joining us. I wanted to talk about, though, from this is the lightning round that's coming up next month. I haven't checked, but we haven't got too many signups yet. But if you have been interested in getting into presenting, this is a really great way to get started. I remember where I did my first couple of presentations, and it was actually just like a full single meetup presentation where I was kind of expected to present for about an hour. And that's a lot to kind of take on initially. With these lightning rounds, we're looking for anything from 5 minutes to 15 minutes. It's a lot easier to kind of fill that amount of time, and also hopefully with a few other people presenting, you don't have that pressure of like, everyone came here just to see me present or showed up just to see me present, as it is with this online format. So it's a lot less pressure. It's kind of a good way to get started. And of course, if you have any questions about that, I'll be more than happy to kind of share my knowledge and experience of having done presenting now for a few years. But it's a really great way to get started. Indeed, Venkat, he actually got started by speaking at his local meetup in, I think it was Denver when he was still, he still is in Denver, but I think he was at the Denver and Boulder meetups is where he got first started. So it's actually how a lot of presenters get started, is through meetups. And one actual real nice thing about doing meetups now is that because they're recorded online, you actually have videos then to maybe share if you wanted to submit to a full conference. And that actually helps a lot, because for the organizers, They just kind of want to know, like, oh, does this person, can they present? Do they know what they're talking about? And so on like that. And if you're just getting established as a presenter and you're kind of submitting to a conference, you don't really know the organizers, having some sort of online video can really help in letting the organizers know, like, oh, okay, yep, they've done a presentation before, and they put something together well. So this would be a really good opportunity. Like, if you're kind of interested in getting started in presenting, this is a great opportunity for that, just because we'll have your video as well. So Alex, you wanted to have a question about Kansas City. Well, we're home of the Super Bowl champions. So, that's pretty great. Also, the world's best barbecue. So a lot of things going good for Kansas City right now. Let me get this. Whoops. Let me get this link posted into the chat here. But you can sign up at that link to present. So definitely give it a shot. Oh, and one other thing I wanted to touch on with that is that don't feel like it has to be some really advanced topic like how Venkat is presenting on fibers. It's not always necessary to have like a very bleeding edge topic. About 3 years back, two or 3 years back, I wrote an article on how to test logging on Medium, and it's been by far the most popular post I've ever done. I consistently get about 300 views on it a week, and that's, again, 2-3 years later. It's been just that consistent level. So it's not like you have to do something super new to be to have like interest. You have something like you've covered that is also similarly just like, oh, here's just like some cool thing I did that really helped me. So you probably have something like that as well. So good news, you're not gonna have to hear me blab anymore. The great Dr. Venkat is here, so let me go ahead and bring him in. Add the stream.
Hey, Billy.
How are you?
Greetings to everyone there. Thanks so much for having me there, and I hope everybody is doing well and staying healthy.
Yes, I hope so as well. I think, no one here, at least we're all distancing online, so no risk of transmission in that way. So I think everyone is probably already tired of me talking, so I will actually pass it off to you. Let me add that to the stream.
And so you're saying that I should take them tired and make them tireder.
Exactly. I got them all revved up for you.
Well, you know what? Here's the good news, right? There's a game after this, as I understand. It can only get better from here, I would think, right?
Exactly. So, so that's a positive spin on it.
Yeah, let's get to business. Let's talk about some fun stuff. Yeah, go ahead, please. Did you have anything to say, Billy?
Sorry, I accidentally removed you from the stream instead of myself. Now I'm going to remove myself from the stream again. So sorry.
Sounds good. Well, along the way, questions, comments are definitely most welcome. So if you do have a question or a comment, please post them on the chat, and I'll try to respond to them as soon as I see them. And if I don't, if Billy would be so kind enough to read that off, that would be great as well. It's not an interruption at all, so feel free to jump in and raise the questions or comments. I'll be more than happy to respond. Awesome. So with that said, I cannot tell you how excited I am about where Java is heading in terms of continuations and fibers. I'm a person who is really excitable, as a lot of people know, but you can imagine my excitability pushed to the higher level. That's basically what continuation fibers are. Now, before we go into the topic, I want to quickly mention this is still further away. So if you're looking for something that you can use on what is today, Thursday, if you want to use something on Friday morning, that's not this. Well, the reason I emphasize that is this has been in development for a while, and it might be a while before we can put our hands on it. And even when this becomes available, It might be a little longer before we can use it. By the time our libraries and dependencies and products really come together to be able to support it. So while this is really great and amazing, it's going to take a while before we can really enjoy it. But having said that, this is something that I've been looking forward to. And one quick note, whatever I say here can and will be wrong, because obviously this is a product in development. I've caught up with it as much as I can, but that doesn't mean it's the state as it is now. So take it with a grain of salt. And eventually when this is released, hopefully we get closer to things. But let's get to what this is all about. Now, when it comes to creating applications, we often program in single-threaded applications. Now, single-threaded applications are easy to understand, easy to design, easy to write code and maintain it. Now, how do you know you're working on a single-threaded application? I'll tell you how you know. You know you're working on a single-threaded application when you go to work and people actually smile at each other. You go to work and people go to lunch together as a team. People are nice and social. That's a sign you're developing a single-threaded application. Then one day somebody says, we got to improve the scale. Let's go ahead and bring in multiple threads. That day, when you bring multiple threads, is the last day anyone smiled at each other on your project, isn't it? Because a code that was easy to work with suddenly turned into a monster right in front of you. And that becomes a disaster to work with after that, isn't it? So as a result, it becomes very painful for us to work with. And so what do? And the idea really is to make this a lot easier to work with when it comes to creating applications. One of the terms that I see here is Java is copying from Kotlin. I quit using the term copying a few years ago. And the reason I emphasize that is that languages constantly learn from each other. And if you really think about it, the Java came about introducing lambdas much later. But the way Lambda was introduced in Java using invoke dynamic rather, made it so much better for all languages on the JVM. So this is the fun part of being on a system like this is it's learning from each other and pushing the boundaries. And remember, Kotlin was not the first language on planet Earth. There are other languages around that have brought in things as well. So I often say this is the experience of learning from each other than copying from each other. And we definitely want those improvements because we are improving the overall world of development by doing so. So when it comes to threads, of course, how many threads can we create? Well, unfortunately, there are two answers to this question. The first answer to that question is it really depends on how much memory that we have. So the more memory we have, the more threads we can create. The less memory we have, fewer threads we can create. But unfortunately, that's not the only thing. It also depends on the number of cores we have on the machine. So it turns out to be a combination of those two. As an example, if you really think about it, suppose your tasks are computation intensive. If the tasks are really computation intensive, then you can have as many threads, if you will, as the number of cores on your system. Why is that? But that's an upper limit. The reason it's an upper limit is if you have computation intensive task, if your threads are busy running, and if you create more threads which are computation intensive, these threads want the existing threads to take a break so these can run. I'll give an absolutely silly example to illustrate this point. You know how monks are the politest people on earth. So monks always look out for others. They always are kind to each other. Imagine there are 4 monks. This is the equivalent of the dining philosopher problem. This is 4 monks on a treadmill. So that 4 monks go to the gym. And the monks realize that there's only 2 treadmills available. So they all kind of have a debate, and 2 monks get on the treadmill. And they start walking on the treadmill. Now, just as soon as they start walking, the 2 monks look around and see that the other two monks are waiting. And they're like, oh my gosh, I'm here using the treadmill when you are waiting. Let me take a break. It's your turn to be on the treadmill. So these two monks get down, the other two monks get on, and they start walking. And immediately they look and say, my gosh, you're waiting. How rude of me. Let me yield for you. So the monks are getting on and off the treadmill, and nobody really gets exercise other than getting on and off the treadmill. This is exactly what happens to code when you have competition-intensive tasks available. And when those competition-intensive tasks are competing for the resource, they begin to trash and you get a poorer performance. On the other hand, if you have more threads than the number, of course. On the other hand, if you have IO-intensive operations, then the number of threads that you can have is less than or equal to. The same formula applies to the top one as well, but it turns out it's equal to a number of cores, if you will, divided by 1 minus the blocking factor. So you have the blocking factor sitting here. So you have the number of cores divided by 1 minus the blocking factor. So in this case, of course, what you have is if your threads are competition intensive, the blocking factor is 0. So number of cores divided by 1 is number of cores, the formula on the top. If the blocking factor is 0.5, then you can have twice the number of cores. And if a blocking factor is 0.9, this is like a koala, right? It sleeps for most of the time. Then you can have 10 times the number of cores. But that's pretty grim, isn't it? Because if I have a 256 cores on my machine for the competition intensive, I can only have up to 256 threads. On the other hand, if it's IO intensive with a large blocking factor, in the best case scenario, I can have 2,560 threads at most. Now, this is not even with respect to memory, but this is the power we can go to depending on the core. But ignoring that for a minute, what about the limitations of the thread? Now, remember, going back to time, what did we have on at our hands? We had processes. So processes, unfortunately, are very expensive to create and kill. In generally speaking, right, we are working towards minimizing that in current days. You have various solutions that are trying to make processes less expensive to start, especially with function as service. This becomes really important. But we all can agree that they are heavyweight, right? Heavyweight processes are generally heavyweight. What about threads? Well, threads often are considered to be lightweight. Now, unfortunately, the term heavy versus light is a relative term. Now, you could be lifting a child, a baby, and you could say the baby is lightweight. Now, it depends on who is lifting and what you're lifting as well. So these terms are really relative. It turns out that a thread is lightweight compared to a process. But as it turns out, threads are not really that lightweight because threads occupy memory as well. And so there is a limit to how many threads you can actually create. Let's look at an example. And this example, I'm going to revisit towards the end of this presentation again one more time. But for now, let's create a function. Let's say public, let's say in this case, static void. Let's call it as do work, nothing really exciting. But within this function, I'm going to say try and let's say thread.sleep, let's say 10 seconds. And I'm going to sleep for this 10 seconds and do a catch exception EX. This is an absolutely trivial example, but nevertheless illustrates the point. So I'm going to say max equal to 10. And then I'm going to say in here, a thread is equal to null. And for int I equal to 0, I less than or max, and then let's say I plus plus. And all I'm going to do simply is to say thread is equal to new thread. And I'm going to specify the sample do work function. And I will ask the thread to be started at this point. So once we start the thread, we will simply say started right there. And then let's go ahead and say thread.join and wait for it. Now, of course, Java is going to ask me to handle the exception, but as experienced Java programmers, we know exactly how to treat that. So we'll simply say throws exception and be done with it for now. Now, this code is not doing a whole lot, honestly, but all it's doing is creating 10 threads and waiting for the threads to complete by just waiting on the last thread. That's all I'm doing. So nothing really exciting. What is going to happen if I were to run this code? What are we going to see as a result? Well, the answer to that question is, let me go to where my code is sitting in this case. So I'll go to the Java directory, and within the Java directory, let me go to where the code is and run this code on the command prompt. So when I run the code, it says started, and it's waiting for the threads to finish, so nothing really exciting. Now, what is really interesting about this code is it's not doing a whole lot. So we're not using much resources, really nothing. But I'm going to go back here and say, hey, give me about 1,000 threads for me, please. So I go off and execute this code right now, and you can see that it started the 1,000 threads, not a problem. Hey, what about if I ask for 2,000 threads? Well, now when I go back and execute the code, it starts 2,000 threads. That's not a problem either. What if I ask for 3,000 threads right now? Well, you notice that with the 3,000 threads, that's not a big deal. The program says I can handle it, and it started that as well. Now, what if I ask it to do 4,000 threads? I feel like an auctioneer right now, which is kind of horrible. But the point really is that I'm able to start 4,000 threads also, so that was not a problem at all. However, I'm asking you to create a 5,000 threads right now. And when I do that, unfortunately, it blows up. What does it say? It says main out of memory exception, unable to create native thread. You know what's funny? It says possibly out of memory. It's not even sure why it failed. So possibly out of memory or a process resource limitation reached. Now, that's because threads are not as lightweight as we would really like them to be. Well, here's a code. I'm going to just save that away. We'll come back to this code later on and take a look at it. So let's go ahead and copy the sample.java to, let's just put it as th. We'll come back to that, look at it. Well, so we see that there are limitations to how many threads we can create, whether it's memory or the other formula we talked about. So where do we go from here? Well, the problem really is that we are trying to create applications that will have better performance and be more responsive. Now, generally speaking, we do multi-threading for us to really make the applications either more responsive or better in performance or a combination of that. That's the purpose of really doing this in general. So the question is, how can we really improve the performance of code? Well, in Java especially, we have been focusing a lot more on parallelism and multi-threading. Don't get me wrong. My dissertation was related to parallel processing. I love parallel processing. But it doesn't matter what I like. What does the world want today? We live in a world of microservices and distributed computing, not as much as parallel, but more of asynchronous communication is needed. Now, in that regard, we want to really focus on concurrency and parallelism in a different way. But what is concurrent? What is parallel? What are the differences between them? Let's think about this for a minute. So let's talk about these two concepts, which is parallel and concurrent. So what is parallel? Parallel is when two tasks can progress at the same time. So in other words, you get two things that are progressing at the same time. I don't have much of a degree of freedom here, but I will try to do the best we can. So here I am, and I'm talking and I'm walking at the same time. So I have the ability to carry out these two operations in parallel. I am walking, and I'm not taking one step and then saying a word and then taking one more step. No, I'm able to do both of them at exactly the same time. So that is parallel. On the other hand, concurrent is where we can say two tasks make progress over a period of time. So notice that we are saying over a period of time, two tasks are making progress. So as an example, when I'm speaking, I am also taking a sip of water, I'm not really that good. I'm not good at speaking and drinking water at the same time. And if I try, it can have a disastrous effect. That's not a good thing. But if you notice, for an hour, I've spoken several words and I've also emptied half a glass of water. So, in other words, I'm speaking and drinking water concurrently. I'm not drinking water for 5 minutes, emptying it, and speaking for 20 minutes. I'm speaking for a 30-minute period, but in the 30-minute period, I am speaking and drinking water, speaking and drinking water. I'm only doing one thing at a time, but I'm progressing on both the tasks over time. That becomes concurrent. The reason this is important to keep in mind is when we deal with these multi-threaded systems, we might be concurrent, we might be parallel, and it's important to know this distinction. But how do multi-threaded code actually work today? Now, imagine you have a multi-threaded code. When you call a function, if the function is blocking, you're holding the task and the thread hostage. Now, let's think about what that means in the context of working with functions with a really silly analogy. Now, let's say we go to work. Now, we all can agree the very first thing we do when we go to work is literally dropping our stuff at the desk and getting a cup of coffee, isn't it? Because without it, we don't function too well. But how do we get a cup of coffee? You go to the coffee machine and you realize the coffee machine is empty, and you turn on the coffee machine, throw the things that it needs inside of it, and you press the button. And do you ever just stay there and not move at all? And you're staying like the person in the front of Buckingham Palace. And your colleagues comes around and says, "What are you doing?" And they try to talk to you, but you don't respond. And then they realize, oh yes, you will not talk until you get your coffee. I assume we don't do that. What we do instead is we turn on the coffee machine and grumble about it and say, "Gosh, there's no coffee. I'm going to turn it on." And you go to your colleague and say, "Hey, you're ready to talk?" And your colleague says, "I need 10 minutes to get ready." Like, fine. And you come and turn on the email. It's downloading the stuff, and you are like, "Gosh, you know what? The coffee machine is brewing coffee. My colleague is not ready. The email is downloading. Let me look at this report really quickly." If I ask you, what are you doing? If you are the thread, you are in 4 different places. You are getting coffee, you're ready to talk to your colleague, you are downloading the email, and at the same time, you're reading that report. And this is how we do things, but that's not the way Java threads work. So what do we do in a single threaded application? You launch a thread, and the thread gets stuck. Now we are like, I launched a thread, it got stuck. I want to scale, so I'm going to create more threads. Why? So more threads can go get blocked and get stuck. And you kind of wonder, is that really scaling? How could it be scaling when you send more threads to get stuck? We need to rethink about it. When threads get stuck, what do? You scale horizontally. And when you scale horizontally, you are moving into cloud computing. I'm not saying cloud computing is bad by any chance, but if you're forced to move into it, you are using a cluster of machines to do your work because you cannot do that on a smaller machine. And this only makes the cloud computing world richer and makes us poorer because we got to become elastic even though we don't really need it. Well, the reason we need it is because of the deficiencies of the environment that we are working with. So the question is, what can we do about it? The answer is, maybe we should rethink about how threads actually work. So before we get to it, let's talk about continuations. What an interesting term, but what is a continuation? Well, first of all, we all know what subroutines are. Subroutines are functions you call and they return a response. I'm going to use an example in JavaScript. I know that's scary, but I think we can learn from everything in this world. So let's go to JavaScript for a few minutes. So here is a JavaScript. And in this JavaScript, I'm going to call a function to begin with. So what does this function do? Let's say this function is called let's talk. And the let's talk function is just a little function as you would expect. And I enter the function. So I'm going to say entering. That's all I'm going to say. And then in the end, I'm going to say, exiting. So awesome. That's entering and exiting the function. Now I can come here and call the function let's talk, and I can call it again, and I can call it again. So I've called it 3 times, and you've entered, exit, no big deal, what we would expect. But this is literally a subroutine. So a subroutine or a function, you enter in the top and you exit in the bottom. Even if you have a return, you've exited somewhere in the bottom. But the point really is that's a subroutine. But a coroutine, on the other hand, is where you can enter and exit multiple times. Now, in a way, this is kind of like the conversation we normally have with people. Now, imagine for a minute that I saw you yesterday and you were walking out the building and I asked you, where are you going? And you say, I'm going to go finally watch that movie I've been postponing, and I'm going to watch the movie. Now, today morning, I run into you and I ask you, hey, did you go to that movie? And you say, yes, I did. And I ask you, how was it? Now, notice, as intelligent people, we continue this conversation. I say, how was it? You say, it was great. And I would say, who were the actors in there? Or what's your favorite scene? And notice we are able to have this conversation back and forth. Now, take this idea and talk about how we can implement web applications with this. Now, today, I would say the way we develop web application is, I have a term for it. I say it's like programming with Dory. Now, remember Dory from Finding Nemo? Every few minutes, hey, I'm Dory, how you doing? And that's what we are doing right now, is we make a request, we establish connection, it's stateless, it gives a response, and we establish a connection again. And artificially, we are throwing a cookie on top of it, but essentially it's a stateless protocol. What if this can become really conversational? You go to a website, it sends a response, but when you make a request again, you continue from where you left off. This can make a very big difference in how we can provide these applications and build the context and build on. So this is where coroutines really come in. So what does a coroutine actually do? A coroutine has a multiple entry point and a multiple exit points, if you will. Let's look at an example of how that would feel like. So in this example, I'm going to turn this into what's called a generator. And when I do, I can say for constant value of let's talk, and I'm going to simply come in here into the loop. But when I execute it, notice it says entering and exiting. Well, that's great so far, but I'm going to say in the loop. And when I say in the loop, and if I run the code, it is in the loop, but I haven't given any values to it. But I'm going to go back here and say yield, let's say a 0. So when I run the code, it says in the loop, as you can see. But I'm also able to print the value, if you will. So I can say in the loop, loop with, and I'm going to simply print out the value that's given to me. And it says in the loop with 0. Let's go a little further with this. I'm going to come down here and say output, welcome back 1. And I'm going to then say yield and put a 1 right there. Now, along the way, I'm going to repeat this a few more times. So I'm going to just repeat this a couple of more times. And I'm going to say this is welcome back 2, if you will. And then I'm going to return a 2, nothing really related to each other. And I'm going to say welcome back 3. And I'm going to return some value of 3. But when I execute the code this time, notice we entered once, and we then are leaving on line number 3. We went to the loop on line 3, but we entered back on line 5. We left line 6. We came back in 8. We left at 9. We came back at 11. So in other words, our function is like this. We enter, we execute, we leave, but we come back where we left. We do some more work and leave, and we come back where we left and do some more work and leave, and we come back where we left and do some more work. So in other words, this is kind of interesting to see how all of a sudden this entire highlighted part has been captured. And imagine in your mind, right there, you're returning a tuple. The tuple you return is the value 0 plus the body of this code, if you will. And you use the tuple's first value, you call back into the code, and the code executes that part, now returns a tuple with the value 1 and the highlighted code as the second part. that jumps right back to where you called, and now it returns a tuple with 2 and that part of a highlighted code. In other words, you are returning back not just the tuple, not just the result, but a result plus a code, so you can use the result and call back in the code. Now, step back for a minute. We all understand there are two things in Java or in functional programming: lambda and closure. So what's a lambda? A lambda is a stateless anonymous function. A closure carries the state with it. Conceptually, you can think of this as a closure. Now, when you make the call to this function returns a data and a closure. You use the data and call the closure. The closure executes, returns a tuple with data and another closure. So continuations conceptually can be thought of closures because they capture the state. But it's horrible to program at that low level. We'll get tired and it'll be error prone. So what is continuation? Continuation is a data structure that can remember the state of a previous call and can continue from where it left off. So continuation is a low-level data structure that will remember the state of a previous call and continue from where you left off. So how does this feel to write code with continuation? So to understand this, let's take a quick little example to see this in action. Well, for this, I'm going to bring in Kotlin so we can see how this actually works in Kotlin. And in the case of Kotlin, I can demonstrate here both the concurrency and the parallelism quite easily. So let's take a look at an example. I'm going to say run, and within run, I'm going to call do work and pass a 1 to it. I'm also going to call do work and pass a 2 to it. And then I'm going to simply print out, let's say, called the 2 tasks. And I'm going to also report a thread dot current thread so we can actually see which thread it's running in. Well, in this case, I'm going to say the function do work takes a number. And what I'm going to do here is to print out, let's say, entering, and I will print the number. And then I'll also print and say exiting, and we will print the number. So when I run this code, it's not doing a whole lot. However, I want to print the thread information as well. Sorry, I forgot that. So let's go ahead and put a few dots here and say, in this case, thread dot current thread. Similarly, I'm going to go ahead and put the same information here as well, except this is exiting, so we can actually see that. But notice all of this is running in the main thread. It is pretty darn sequential, right? So entered 1, exited 1, entered 2, exited 2, call the 2 tasks. This we know is sequential programming. No big deal, single threaded. Well, let's go a little further. Now I'm going to say in here, import, and I say Kotlin x.coroutines.star, and now I change this to run blocking. The reason is this is now a coroutine. And when you run the coroutine, you are saying, hey, coroutine, go execute. Oh, main, don't be in a rush. Wait for the coroutine to finish before you go forward further. So run blocking simply tells the main thread or the calling thread to block and wait for the coroutine to finish. Output is no different from what you saw a few minutes ago, so it may appear like a little bit of a disappointment. So enter 1, exit 1, enter 2, exit 2, calling 2 threads. Notice all of them are in the main thread. We're not doing multi-threading yet. However, I'm going to go back to this code and say launch. And I launch the 2 tasks at this point and say, go ahead and run them. But look at the difference all of a sudden. The output is not the same as before. When I run this code this time, the very top output is calling the 2 tasks. So what just happened? Well, the launch did not do the work. Instead, it takes this task and throw it on a queue. It takes this task, throws it on a queue, and execute that. When it finishes, it says, I'm done. And it says, wait, you're not done. Your coroutine is still having some work to do because your coroutine started 2 children. So this is called structured concurrency. So structured concurrency is where you have a parent coroutine and you have children coroutines. A parent coroutine, even though the code may finish, the coroutine is not done until its children are done. It's like a wonderful parent who puts the children to bed before they go to bed. So the coroutine says, I'm not done until my children are completed. So these two children are pending. So this coroutine finishes but doesn't complete and says, I want to wait for these two to finish. And now it goes to the queue and says, hey, you, let's run you. And then it goes to the queue and says, hey, you, let me run you. So when you run the code, you can see it called the task, and then it entered into one, exited one, entered two, exited two. Now, let's talk about concurrent versus parallel. Well, what does concurrent mean? The two things are progressing at the same time. I want one to progress. Before one finishes, I want two to progress. So one is here, two is here, one is here, two is here. I want them to progress concurrently, not in parallel. How do we do that? Well, you can go back over here and you can provide a yield as a call. The yield simply says, hey, I've got some work to do, but I don't want to hold you for that. A coffee machine. You turn on the coffee machine, it starts brewing, and you say, you know what? I'll be right back. I don't want to wait for this to finish. So you call the yield. Well, we're calling the yield, so you mark the function as suspend to say that this function may not complete entirely. It might actually take some time to come back and finish. So you can come back and resume this function. But when you run this code, notice the output is very different this time. You call the two task, but notice you entered one, but you didn't exit one yet, but you entered two. So right where the line number 6, at the end of line number 6 on the left side, what is on the right side? At that given instance, you are both within 1 and 2. You are doing that concurrently, but all of that is in the main thread. So we're not doing parallel right here. We're doing concurrent. So the thread has done two tasks and progressed on both of them at the same time, much like I've said a few words and taken a few sips at the same time. So you can see here's the number of words Venkat has spoken, here's the amount of water he has completed, and he is working on those two concurrently. So this task proceeded on 1 and 2 concurrently, then it exits 1, and then it exits 2. So essentially, this puts a message on the queue to say, when I'm ready, you can come back and work on it, continue further. Just one more detail before we go any further about this. Now, I'm a little curious about this, so I'm going to get rid of all of that, and I'm going to simply say fun. Let's call it foo, n, which is an integer, and I'm not doing a whole lot in this function. I'll just leave it empty right now. Well, maybe all I will do is return n times 2. How about that? So let's go ahead and just return it so it doesn't give us warning and all that good stuff. Here is a little bit of a Kotlin code, but let's play with this. So here I am on the command line, if you will. And on the command line, I'm going to go to the directory where this is sitting, and I'm going to simply say Kotlin C -jvm, and I'm going to compile this. So -d temp classes directory, and I'm going to compile sample.kts. That's all I'm doing. I just compiled that piece of code. Now that I compiled it, you know what? I'm going to blow away the things in the classes directory so I don't have anything left behind to confuse me. So when I run the code, what do I have in the classes directory? So if I look in the temp classes directory, notice that I have a sample class. Let's do Java P -c -p, all those good stuff. They're all aliases on my machine. And I'm going to simply say temp classes sample.class and take a look at the bytecode. I want you to notice this function foo. It looks pretty innocent. It is a public final int foo, which takes an int. Nothing exciting. Great. But I'm going to make one change only. All I'm going to do is to go to this function. Without anything more, I simply say suspend. That's all I did. I didn't do anything other than just add that keyword suspend. That's all I did. Now I go back and I compile my code. And once I finish compiling, I take a look at the bytecode one more time. But this time, look at the bytecode. What do we see? Notice the bytecode, the function foo now returns an object, takes an int as an argument, but it also takes a continuation as a parameter. So in a sense, what just happened here is that this function says, you can call me back with a partial state of execution. So that's why continuation is a data structure that can remember the previous call state, and you can invoke it with that information. So that's basically, pardon me, what we saw so far. In that regard, what if we can do something like what we did here in JavaScript? Look at this function in JavaScript one more time. We are in the loop, entering the loop once, but interacting with the loop until we come out. Well, let's get back to the world of Java. So here I'm in Java. So let's go over here and say that public static void do work. And the do work function, what am I going to do? I'm going to say continuation scope. And I'm going to bring in a scope right there. So all I did was I brought in a continuation scope as an argument into the do work function. Now in here, of course, I'm using Java with Project Loom. So I downloaded the Project Loom implementation, and I go in here and say continuation scope is equal to new continuation scope, and the value is a scope. Then I say continuation is equal to new continuation. Before we go further, where in the world are these things coming from? It is so fundamental in Java now that continuation scope and continuation are actually part of the java.lang. So it's the very top level. So you have a continuation, and I'm going to take this continuation and give the scope to it. And then I'm going to say comma, and I'm going to fire up the do work function and send the continuation scope to it. So that's all I did. I'm going to call this as scope right now, so it's a little easier to see this within the window here. So that's a scope, and that's a scope we are passing. So that's all I did so far. Then I say while continuation dot is not done, what do I want to do? Well, I go up here and say output, and I'm going to say entering. That's all I'm going to say. And then I'm going to say output, and I'll say exiting right there as well. But then I come in here and say output will say in the loop. That's all I'm going to say, in the loop. But then I'm going to say continuation dot run and ask the continuation to execute. So when I run the code, it says in the loop, entering, and it says exiting. But then I go in here, much like the JavaScript code, and I'm going to say continuation dot yield, and I'm going to call the yield function over here. So I do a yield on it, if I know how to type yield today. There we go. And I send the scope right there into the yield. And then I'm going to go ahead and say welcome back one. I'm going to repeat this a few times in here. So let's go ahead and say welcome back one, welcome back two, and welcome back three. And now let's go ahead and execute this code and see what happens. We entered the loop. We entered the function in the loop, welcome back one, in the loop, welcome back two. So I almost simulated the JavaScript example here in Java. So you can see the continuation. You would not write code like this because continuation is a very low-level data structure. You and I are most likely not going to code with it, but I'm a very curious person. I want to know, what does it feel like? And that's basically what we saw here. Well, so that takes us to the next part. We looked at what continuations are. Now we want to talk about fibers, but that's a good time for me to yield and see if there are any questions or comments before we dive in and talk about fibers and what they are and where we are heading with this. So any questions or comments that you may have, I'd be delighted to hear your thoughts, your voice, your questions.
And just so you know, we do have a couple of moments of delay. Not seeing any questions yet, but so it might be a few moments.
Okay. Yeah, there's a bit of a delay.
Mm-hmm.
So let's see if there's anything at all. Thank you. All right. So let's go on a little bit further. And if there's any question, please do bring that up, or any thoughts or discussions. Don't hesitate. I'll be delighted to hear what you have to say. Well, now let's talk about fibers. So different languages call these differently. Some languages call it, question, Brandon, thank you. Does the JVM reuse threads under the covers? So let's step back for a minute and talk about it. In the JVM, before we get into fibers, in the JVM, you are using kernel level threads. So literally, when you are firing up your JVM and you're creating threads, those threads map over to the kernel level threads. And as a result, your threads are mapping to the kernel threads, and as such, there's a limitation. And as a result, you are bound to what your kernel threads are going to do. So if your threads are busy running, and if your threads are blocking, as a result, you are actually going to have a poor use of the resources. So as a result, if you want to scale, often it forces you to go across machines for that reason. So the answer is threads are reused, yes, but when a thread is being used, you're also constrained by how much of that you can potentially use. There's limitations to how much you can use. When you're using a thread pool, definitely we are reusing the threads, obviously. So for example, if you're using an executor service, then you latch on task and remove them from the executor pool. And as a result, the executor service can execute multiple tasks in those threads as well. So it depends on the context as to how we actually use it. A comment or a question from Drazen here is, what prevents Java to have coroutines as Kotlin since they run on the same JVM? What are the main issues Java faces now? Really good point, Drazen. Well, the problem really is we have to really look at implementations and decide whether those are adequate. So the first question is, when you are writing coroutines, let's talk about Kotlin for a minute. When you're writing a coroutine in Kotlin, Kotlin gives you the mechanics for creating the coroutines. But when a coroutine is running, imagine you call into a function that calls into a database. We're purely talking about Kotlin right now. So you're calling into a function that calls into a database. You're calling into a function that calls into a remote web service. If those calls block, your coroutine thread is going to be blocked. So Kotlin magically does not give you the ability to change that behavior. We need more things beyond that. Now take those ideas, bring it to Java. In Java, you already can spin threads. We know that. But you can do coroutines. Well, in Java, you can do multi-threading. In Java, you can also create completable futures. But the problem is, what happens when you call a function that blocks the thread? So Java cannot let you spin threads or spin coroutines and say we are done and walk away, because that won't give us the solution. So what Java had to do, and this is where the real complexity is, they have to painstakingly take every single function and make them non-blocking under the hood. And that's not easy. And I'll come back and talk more about this a little few minutes, but you cannot just walk away by providing a mechanism to fire off coroutines and walk away, because you need also to know what to do when you call functions that are going to be blocking. In other words, Java has to painstakingly convert all the functions to non-blocking functions. So when you call the database a query, or when you call into a remote service, you don't want that to block your thread. That has to be done, and it's not going to happen magically, right? So they have to rework all the code for doing it. That's painstaking, because you got to examine every function and make it possible for it to do that. That's the complexity you are dealing with. So it's easy for us a lot of times as programmers. to look at a syntax and look at a feature of a language and be convinced that that's easy to do. But it's not, because we need to think a lot deeper about the consequences, the performance. I will use the same analogy again. When Java wanted to introduce, let's ask this question for a minute. Scala had lambdas for nearly 11 years before Java introduced. Groovy had lambdas for 11 or 12 years before Java introduced. So let's ask the same question you asked. I'm not blaming you for the question at all. It's a very good question, but I like to really understand these questions in a slightly different sense. So the same question I asked once. I asked the question, if Scala can do lambdas, if Groovy can do lambdas, why can't Java do lambdas? Well, the reason is, if you look at what Scala did back then, if you look at what Java did back then, they implemented lambdas as anonymous functions. That simply doesn't cut it. So Java had to take the time to innovate the invoke dynamic. And once they came up with invoke dynamic, we don't have the cost of creating lambdas. And suddenly Scala 12 uses the invoke dynamic of Java. And so that's kind of the equivalent here, right? So Kotlin has coroutines, but Java has to go back and see what are the consequences of bringing that over, just like they had to go through in lambdas. So there are implementation issues that you have to deal with, that you have to be very careful about when the Java and the JVM are going to accommodate something. And I'm not making this light of those languages, but I cannot also look at what those languages do and assume if they can do it, Java can do it. No, because the expectations are very different on Java and the JVM compared to these languages, and that is one of the consequences. A really important point. I'm glad you brought that up. That's something to think about. So with that said, let's go a little further with this and talk about it. And that is, what are really fibers? Well, different languages call these differently. Java doesn't call this fibers anymore. So what Java calls these from now on is called virtual threads. So virtual threads really are fibers. So what are virtual threads? What are fibers? Well, they are super lightweight threads. You say, oh my gosh, why is it super lightweight threads? Because lightweight threads are taken, right? So threads are lightweight. Well, because threads are lightweight, what are fibers? They only can be super lightweight. Well, unlike threads, fibers do not take as much memory. They do not take as much resources. And as a result, so question or comment here, continuation fibers are supposed to be to replace completely with future and threads. Well, they're not going to be a complete replacement. They're going to be an alternative in a lot of different areas. So I'm not going to say that they will never be, they as in completable futures and threads will never be used. What's going to happen is they're going to manifest into something more meaningful, because you still have to worry about, Louis, you have to worry about still passing the data around. And for that reason, completable futures may be useful. So maybe completable futures will morph differently so that they become available to run using virtual threads and fibers rather than regular threads. So there's possibility that they may coexist, they may morph into a different thing. I don't know the answer at this time, because those are things that has to be resolved moving forward. So they're not a replacement, but there are times you may use threads, there are times you may use virtual threads, and you may go back and forth depending on what you do. And as we go on, I'm sure we're going to learn more about it and see where it takes us. So with that said, the fibers are super lightweight threads, and they are managed by the JVM and not the operating system. So unlike threads, which are kernel threads, they run at the operating system level, the JVM threads are not such. So they are only within the JVM, completely managed by the software internally by the JVM. And one of the key things to keep in mind is this. So imagine the world of threads. You have a thread, and my bottom hand is the thread, one that is flat and open facing up. My palm is facing up. That's my thread. I take a task right now. I put the task on the thread, and I'm running the task on the thread. Now my task says wait. I'm going to call into the database wait. So my task is waiting. What does my thread do? My thread is waiting. This is a coupling we are dealing with right now. So what do? You take a thread, you put a task, you send it. The task is stuck, the thread is stuck, and you're like, okay, you wait over there. I'm going to create another thread. So we create multiple threads so we can run multiple tasks on them. Now, this is not efficient. Think of a waiter in a restaurant. Now, a waiter in a restaurant, think of a waiter as a thread for a minute, logically speaking. So the waiter comes to your table and says, how's it going? And you say, could I have some water, please? And the waiter says, I'll be right back, and goes to get you water and says, here's your water. Can I help you with something else? And you say, I am kind of thinking, would I want to order this or would I want to order this? I'm still not sure. And you turn to your friend who is next to you. What do you think? Which one do you think I like more? What does a sensible waiter do? The sensible waiter doesn't get stuck at your table and say, let me wait for you to decide. A sensible waiter says, hey, dude, why don't you take a minute to think about it? I'll be right back. And leaves and goes serves other tables. This is exactly what we are looking for. Here's your thread, and here is your task running on a virtual thread. Now, when you run this, your task says, wait, I'm going to make a call to the database. I need some time. And the virtual thread says, okay, you can wait, but I'm going to detach the real thread from me, and I'm going to go do something else. So in other words, look at this as a mapping. So you are mapping your task, which is attached to a virtual thread, with the real thread. When earlier on, when a task is blocked, your thread is blocked. Now, your task is blocked, but your thread is detached. And your thread goes away and says, I'm going to do my work. You can take your time. When your task finishes, it says, I'm ready. And then the operating system, the JVM says, oh, you are ready. I get it. Hang on a second. Let me find a thread for you, and I'm going to give it to you so you can execute it. Much like in a restaurant, you might have one waiter serving you, but you are low on water. Another waiter who is buzzing by pours water and goes away. So you don't adamantly say, you're not my waiter. I'm going to wait for my waiter. Well, you want water. Who cares who gives it to you? So in other words, basically you can have this non-blocking. So when a fiber blocks, the task waits, or actually when a task blocks, the fiber waits, but not the underlying thread. So this is a detachment from the model we had. And so how do we go about using the fibers? Let's take a look at an example really quickly in here. So what I'm going to show you here is, once again, my do work function. So public static void do work. And within this do work function, I'm going to say output, let's say called from, and I'm going to display right now the thread dot current thread. I'm going to display that. And then plus, let's go ahead also and say a thread dot is virtual, and I want to really know if it is a virtual thread or not. So what is the thread? Pardon me. So I'm a little too eager to write it. So let's go ahead and say, in this case, var thread is equal to thread dot current thread. And then I'm going to say this is going to be the thread itself that I'm displaying right now. And then, of course, I'm going to display if the thread is a virtual thread or not. So that's all I'm going to ask for. Okay. Then coming back here, let's go ahead and say thread is equal to and new thread. And let's go ahead and say sample. And then we will ask the sample to execute the do work function right there, the thread to execute it. Then we say thread dot start to start the thread. And once we start the thread, let's execute it. And I'm going to simply say over here, started as an output. And then let's go ahead and say thread.join and wait for it. Now, clearly, we need to handle the interrupted exception. So we'll say throws, and we'll say exception and be done with it. So when I execute this code, what's going to happen? So when I run the code, it says started. Notice it says called from thread 05 main, and notice the word false. It's not a virtual thread, it's a real thread. Great. Now, I'm going to go back to this code one more time. And this time around, I'm going to say this is thread 1. Let's call it thread 1. And I waited for thread 1. But then I'm going to say right here, thread 2. And I'm going to say output, again, started will output that. But then I'm going to say thread 2.join and wait on it. But what about thread 2? I'm going to say thread.start virtual thread. So I start a virtual thread and I simply pass sample do work to it. So compare line 17 with line 11 and 12. In line 11 and 12, we create a thread and started it. In the case of line 17, we already started a virtual thread at this point. So now if I go back and fire this up and execute, notice that the top one is still a regular thread, but the bottom one says I'm a virtual thread and I'm running in the fork join pool 1 worker. And in the last part says true, I'm actually a virtual thread. So what we did here is we created a virtual thread at this point rather than creating a regular thread. Now, what are the benefits of doing something like this? The answer is we want to be able to run these threads, but what about the issue of calling functions? How do they actually work? Well, to understand this, let's take a look at a slightly different example. So let's say we have a function called getResponse. The getResponse function is going to make a call to a URL. It's a URL that's simply going to return back the status of your request. So I'm not really talking to any significant service, but a useful one to call. So what am I doing? Sending requests from, and I say the current thread. And then what am I doing? I call the scanner and I do an open stream. Going back to your question, Drazen, is if you look at this, the open stream has been modified in here. And as a result, this open stream will block your virtual thread, but will not block your real thread. So as a result, when you stop on this, you're not going to be blocking on your resources. So you can scale a lot better. Whereas you can maybe have a few thousand of these requests. Maybe you can have millions of these as well, because you send off a request, but you're not holding anything on your side as a resource. So then when the response comes back, you wake up from the response and you execute this in your virtual thread. So how does this feel to call that function after all? So let's give it a try. So I'm going to say thread th is equal to new thread. And I'm going to say, in this case, sample get response, which is what I want to call. And then I'm going to say thread.start. And then I'm going to say thread.join and wait for the thread to tell me that it's actually done. So if I execute that code, what am I going to see at this point? Well, clearly, in this case, I need to import java.net.star. So let's give it a try. And scanner, of course. Let me try to do that again. So this is the util that was there. But I'm going to bring in the Java. So bring in the Java net as well. So import java.net.star. So when I run the code, what am I noticing in this case? Oh, of course, friendly exception. Let's take care of that. So that's throws exception. There we go. Are you happy now? Okay, let's try this. So when I run the code, yeah, it's a main and main, right? No big deal. But that main thread was blocking and waiting for the response to come back, even though that was pretty fast. However, I'm going to go back to this code now and remove this and simply say, this is going to be thread.start virtual thread at this point. And when I run the code this time, what am I noticing? Notice that in this case, the output says that we started out and we have a fork join pool thread that's using, but it's a virtual thread. It made the call and the receive comes back from the virtual thread. So as a result, we can see that we are not really using the main thread at this point, we're using the virtual thread. But the point really is when it calls the OpenStream function, that thread doesn't block the underlying thread of execution. So the operating system threads are used more effectively rather than blocking. And so as a result, it becomes a lot better. Well, so if that is the case, what does it really mean to use virtual threads? Well, the first thing I mentioned was when you make the call, they had to painstakingly make all these functions non-blocking. So they are not blocking your thread, they're blocking your task. And notice that when you make this call, it's going to get the result at this point somehow. But when it gets the result, the rest of the code has to deal with it. So when the thread is ready for execution, it is going to restore its state and be able to use the function. And also remember lexical scoping. So when you come back from the call asynchronously, you're able to pick up and run based on the context of variables. So going back to your earlier question, Louis, about completable futures. Well, completable futures are amazing, but the problem with them is you are building a pipeline of calls in a completable future. You have one stage, and then the next stage, and the next stage, and the next stage. In the imperative style of programming world, this is not easy to deal with for exceptions. It changes the way we perceive. You structure the code very differently. And that's a problem. Now, I want to say, so your question was, are they a replacement? I want to think about this a little bit differently, if you will. So I want to think about this. What were really streams, if you will? So I will say, before the time of streams, we lived in this world, and that is the structure of sequential code. Sequential code is very different from the structure of concurrent code, right, or parallel code. So this was very different if you think about it. This is the world we lived in. You write the code sequentially, and then you go out for 3 months on a different project. You come back, your team said, we introduced multi-threading. Now you're like, my God, I cannot recognize the code anymore. This is the world we lived in. So this was the past. But then, what did Java 8 do for us? In Java 8, you have streams. So what do streams do? The structure of sequential code is the same as the structure of parallel code. This is the contribution of Stream API, isn't it? What was amazing, isn't it? So what did we do? We can say some list.stream, and then what do you do after this? You say filter, and then you say a map, and then after that you say maybe another map, doesn't matter, and then you write more, and you say, okay, that's my code, and you say I want to run it parallel. Well, you simply come here and say parallel, with proper consequences, and notice the structure is exactly the same. That was a contribution of Stream API. So my question now is, what about coroutines? What do they do? And I'm going to say the structure of synchronous code is the same as the structure of asynchronous code. So this to me is the marvel of coroutines, is that it gives you this ability where the structure of synchronous code is the same as the structure of asynchronous code. So you write your code, make it work synchronously, and then you say, I want to run this asynchronously. Hey, no problem. You don't have to change the code drastically and jeopardize your structure in order to go asynchronous. To go back to your question, Louis, is the structure of completable future is totally different compared to the structure of sequential code. And as much as I love completable future, that's the drawback, isn't it? If I write a sequential code and you tell me, Venkat, change it to completable future, and I change it, and you come back the next day and say, what in the world is this? And I say it's the same code. And you're like, my gosh, it looks very different. And that is the nature of completable future. But what if we can use coroutine where the code structure is the same, and you look at it before and you look at it after, and you can reason with it very nicely? That's where we want to really be. So the last thing I want to show you to that effect is going back to the code we wrote in the beginning when we started this out. So let's quickly take a look at the code we wrote that we had a minute ago. And so it is the code where we were creating these threads. So right there, if you remember, I was able to create 4,000 threads. And going back over here, let's go ahead and run that. And you can see it says started. That was not a problem to create 4,000 threads. A really silly example. But when I try to create 5,000 threads, that's what we saw in the beginning, it exploded. It is out of memory error, couldn't do it. So now the question is, how do virtual threads really help us? Now, before we go further with that, I want to show you one more thing, if you don't mind. So I'm going to go back to this code, and I'm going to just open up a command prompt and run that in that second command prompt. So in this case, the code, oh, pardon me, I forgot. So give me a second. So I want to go back to this code right now, and I'm going to change this to, oh, darn it, this one, right? 4,000. So now I want to go back and run this code again. So let's run that. You see the code is running, but now while it's running, what I'm going to do here is do JPS, and that's the process right there. I copy that, and JCMD, and I'm going to provide the process thread.print. So I'm going to take a look at the threads that it contains at this time. No such process. Did that finish already? Venkat is too slow to type. Okay, pardon me. I'll try to be a little fast now. So run it again and come back and look at the JPS. I got it. Let's try to copy and paste it. One more time. Come on, Venkat. Faster, faster, faster. And copy it. Okay, there. So what I wanted to show you here was, notice that in this output, I want you to see this line, sleeping right there. And let's do this one more time. So I'm going to go back because Venkat is so slow. Let's change this to 30 seconds. I just want more time for this to run. And maybe if I take another sip of coffee, I'll be a little faster, but not at the moment. So let's go ahead and run this JPS again. And here's the process. So I'm going to go back and run the command and look at the threads. But this time, I'm going to say grep and we'll say sleep. And the point I wanted to make is you can see all these sleep coming through. Thread.sleep, thread.sleep. They are blocking the thread. Just keep that in mind. Threads are sleeping. Okay, great. Now let's go back to the code. Let's kill this. We don't need this running anymore. And we know that we cannot run 5,000, right? That's proven already. So if you put 5,000, that fails. So run this code again, and boom, it blows up. So leave that killed. No need to be worried about it. So kill that and move on. Okay, great. Now let's go back to this code. Going back to this, I'm going to get rid of the thread start really quickly here, and instead say thread is equal to thread.start virtual thread, and I'm going to provide the sample do work. So I just delegated that to the virtual thread. That's all I did, nothing really different. And then I'm joining and waiting for that. So when I go back and run the code this time, notice it says started. That's an improvement already, isn't it? But I want to kind of explore, what number should I give here? Anybody's wish? Be a little kind on me though. But any wish about 5,000? Any calls? Going once? Like an option, right? 200,000. All right, Billy. So 200,000. Is it 200,000? Yes. So let's fire up and see what it does. And well, all right, done. Next one. Anybody with a bigger number? 50,000. Okay, 50,000 right there. And let's fire it up. And 50,000, done, started. Anybody else? How about 100? Well, what is that number? So that's 1 million, isn't it? So Dr. Evil. So that's 1 million right there. And that's basically what we have right now. 1 million threads, a billion. Diego, don't push it. But why not? We'll try it. So there you go. We started it. I'm kind of curious. How much can we go with this, right? So let's put a little bit more to it. I mean, at this point, I'm a little nervous, but let's fire it up and see where it goes. It's probably going to take a while to spin through it. Integer.max int. Well, so the point is, yeah, that's the loop is going to take a lot more to run. And maybe, you know what, I'm being silly here. I don't even know if that's going to be fitting into this or not. That's why integer max int makes sense. But the point really is, even go back to 1 million threads or even 2 million threads, right? But the point really is you're able to fire up that many threads, as you can see. Let's go ahead and kill this one. So JPS, oh, it killed already. Okay, so now let's go back and fire this up. This is 2 million threads, and I'm running that and asking it to start. And with the 2 million threads, you can see it can start as well. The point I wanted to make was this, oh, pardon me. One more thing I wanted to show you here was, remember, we fire up with 2 million threads. They are running right now, but this time I'm going to do JPS, and here's my process. Now I'm going to go back here and look for the sleep, if you will. So going back over here and check that process, did you see that? There is no sleep at all, even though we are using sleep. Why? Because it is not really putting the main thread to sleep. Instead of putting the main thread to sleep, instead, it's a virtual thread that's sleeping. So it's like the kid takes a nap and the parent goes off to do things. Or the examples on GitHub, no, but I will put them on my website. I'll give you the URL in just a little bit. So essentially what you did here is, so basically you are saying, hey, child wants to sleep, but the thread can go off and do other work. And that's basically what you're seeing here. Comment or question from Brandon here is there a mechanism to explicitly declare that a fiber is blocked or is inferred from the specified JDK API? No, it's inferred from the API. So there is no, at least right now, there is no way to tell that it needs to behave like that. That's the cost, Brandon, is that they have to go and fine-tune every single function. I don't know the answer if there's a mechanism to turn it on and somehow magically say don't be blocking. I don't know. But what they have been doing for the past few years is putting that effort is to go in and change these things. In all honesty, I tried this maybe a year ago. And when I tried it a year ago, remember the example I showed you where I made the HTTP call? That was blocking. It was not non-blocking. Today, it's non-blocking. So they've been putting effort towards it, and they are been changing that quite a bit as time goes on. Another question is what happens when the task gets blocked? The consequence, if it gets blocked, it's going to starve your resource. So at least that's what it is now. Unless we find a way to deal with it, I'm just thinking maybe it could warn us, or maybe there could be an annotation. I don't know the answer for those things. We have to find out where it goes, and we have to figure it out. So Hermer was asking if the code is going to be on GitHub. Let me quickly mention that it's not there yet, but I will post this on my website. If you have your smartphone, you can take a photo of that. Give me until the weekend. I will post that on Sunday. So if you visit my website after Sunday, I will have that posted on my Sunday. It should be the top talk on the website. So you can take a photo of that or note down my email and drop me an email. I'll be more than happy to send you the link if you need it. One more question here is, how can we try this? Which JDK? Do we need to download something specific? Yes. Ankush, the answer is, first of all, be careful because this is not ready for production. But when you go and search on the web and say OpenJDK project Loom, and you will get to the OpenJDK project Loom directory, and I downloaded it much like I download the OpenJDK for 14. It was no different at all. And once I downloaded it, I set that as the installation on my machine to the path. And let me quickly show you, if you don't mind, just to illustrate this point. So if I go to my Java directory, I have a JDK 16, as you can see in here. That's the version I'm using. So right now, it's under the code name 16. So if I say Java minus version, you can see it says 16 version 2021, 316. So the expectation is it might be released in 2021, but don't bet on it. This is just an expectation at this point. And earlier it was a previous version, and that's moved on. But if you just download Java 16 project Loom version, then you want to make sure it does say Loom. then you can use it. And literally right before this talk, I changed my path to this. And I have a little reminder for me to change the path after this talk, obviously, because I don't want to mix this with other things I do. But that's how you can bring it. If you're interested to bring it, you can bring it through that mechanism. So hopefully that answers your question, how to use it. Well, that's all I have. I sincerely hope that this was useful. And this is something that I'm really excited about in terms of where the technology is going. Very exciting times for Java, certainly, and very exciting time for what this is going to do for the world of concurrency and asynchronous programming. I couldn't be any happier than these technologies. This is like a kid in a candy store. I've got a lot more things to play with and learn now, so I'm pretty excited. One more question or comment here. This seems to achieve the promise of FJ's common pool with the work stealing, which couldn't due to the IO blocking stalling of the common pool, which, as you have shown, is being worked on under the covers. Yeah, absolutely. It's very painstaking. You're absolutely correct that it takes a lot of effort for them to do. So when would we not want to use? Oh, that's a really good question. I'm so glad you asked that question, Crimson, or I'm sorry, my eyes are not good. I'm not able to read from here. Well, really good question. I'm glad you asked that. It makes zero sense to use virtual threads if you have computation intensive task, right? If your tasks are computation intensive, it makes no sense, because a computation intensive is going to be number crunching. There's nothing to really yield. And at this point, if you say, I want to use a virtual thread, you got zero benefits out of it. So as a result, it's only useful for IO intensive. When you make a database connection, when you call into a microservice or a remote service, when you do logging, when you do file IO, whatever that requires blocking. Next question here is, what is blocking factor in IO intensive? I call it, that's my term, I call it blocking factor, but it's really the time you spend not using the CPU, but waiting for IO operation to finish. So if I'm doing a computation intensive, my blocking factor is zero. I'm constantly working. If I make a call to a remote web service, it's a slow network call, my blocking factor could be a lot more. So blocking factor to me is the fraction of time you are waiting, not using the CPU. What manages the rescheduling of the virtual thread? Will the JVM ensure that there isn't a thread starvation with the virtual thread? Yeah. So the JVM manages this entirely. So all the virtual threads are managed by the JVM. We haven't covered this, but there's going to be a lot more about how do you perform the scheduling and all of that. So all that will come to light, and then that's going to be handled that way. And the next question here, Ramkumar is asking is, how do you compare continuation fibers with features provided by reactive programming? Really good question. There is no comparison at all in my mind. And the reason I say this is, somebody asked that question in a conference, and here's my answer. Reactive programming used to scale your service. Fibers used to scale your servers. Because the problem with the server is, when you do multi-threading, you are blocking your threads. So to scale the server, you're going to benefit from fibers. To scale your services, you can use reactive programming. Reactive programming is a stream of data, right? That's what you're dealing with. You're dealing with a stream of data. And so you do asynchronous stream of processing. Your services can scale with reactive programming. But your server itself, if that's using regular thread, you're not going to get better throughput on your server. So my observation is, reactive programming scales your service, fibers scale your servers. I hope that kind of answers what the contrast is, that they are completely different areas of performance efficiency, if you will.
Awesome. I think you've gone through all the questions. Thank you so much again, Venkat, for coming and presenting at KC Jug again. I mean, unfortunately, this time virtually, so can't give any barbecue, but hopefully, we'll be able to have a chance again to meet in person. And
it's a pleasure. I really want to thank everybody who took the time to join. These are unprecedented times, but anything that can keep us engaged and active and learning is definitely a welcome. So thank you so much for having me at the group. I really appreciate that.
Yeah, thank you. Looks like we have one more question.
So the limit to the number of fibers is based on JVM memory. Yeah, eventually you'll hit the threshold because nothing is for free. But you can see on this machine, I could not create 5,000 threads, but I was able to go beyond 2 million fibers, right? So definitely there is going to be a limit, right? Nothing is for free. So it's a super lightweight, but not non-existent. It's kind of like it still takes memory. It will, and that you will hit the limit. But I'm really hoping you will not have to hit that limit because before that time, our needs will be very different. I'm hoping so. It will be a big limit, if at all. Yeah.
Cool.
Thank you very much.
Thank you again. Thank you everyone for all the great questions, and hope to see everyone next month. And definitely, if you're interested in submitting on a lightning talk, please do submit. So awesome. All right. Thanks, Venkat. Be safe.
Thank you. Bye bye. Take care.
Bye.
Until meet again.
Mhm.